Since trying to figure out what the change in entropy is can be pretty tricky, I'm going to show you several examples. Here's another example on how to do that. Here we assume that we have a block of ice, 1 kilogram at 0 degrees centigrade, and we throw that block of ice in a lake, a large lake that is at 10 degrees centigrade. What is the change in entropy in this case? So the way we have to think about it is this way. First of all, heat has to be added to the ice to melt the ice. Because once it's thrown in the lake and there's water around there that's 10 degrees centigrade, heat is going to be transferred from the lake to the ice to melt it. Secondly, once the ice is melted, that water that was ice before is now at 0 degrees centigrade, and it will continue to receive heat until it's reached a temperature of 10 degrees centigrade. At the same time, the lake will be giving away or losing heat because it has to melt the ice and heat that cold water up. So we have an exchange of heat that we have to account for. So we can say that the delta S is going to be equal to the delta S of the ice melting plus the delta S of the cold water heating up plus the delta S of the lake losing heat. Now what we could probably say is that since the lake is so large, the lake will not change in temperature, so we can just simply say that the lake is losing heat at this temperature and be done with that part. All right, so this is a pretty good approximation of the change in entropy. Let's now go ahead and put the equation down. So this is going to be equal to the delta Q over T. Now, matter of fact, I probably don't need to go through that step because we already know that by definition that delta S is equal to the change in heat at the temperature which it happens. So in this case, the change in heat for the ice melting is going to be m times the latent heat of fusion divided by the temperature at which this happened. So that would be temperature of the ice. All right, then the cold water heats up. So now we can say that it receives heat of the amount of mc delta T divided by the average temperature, because now we can see that it starts at 0 degrees and it rises up to 10 degrees centigrade, so we can take the average temperature of the water as it heats up. And then finally, we can say plus the mc delta T divided by the temperature of the lake, because we can say that the lake is so big it's not going to change in temperature, so that will stay fairly constant. All right, I'm taking the liberty of not using the equation where I need to integrate because the average temperature is, the difference between 0 and 10 degrees is very small, so we don't have to worry about any residual errors for that. All right, let's plug in the number and see what we get. We have 1 kilogram times the latent heat of fusion, which would be 4,186 joules per kilogram times 80. That was the latent heat of fusion for water changed into ice or ice changed into water. And then we divide that by the temperature of the ice, which is 273 Kelvin. Notice that the kilograms cancel out and we're left with joules per Kelvin, which are the proper units. Now, since the ice is receiving the heat, that is definitely a positive mL sub F. All right, next, the ice that is now turned into water is rising in temperature from 0 to 10 degrees centigrade, so it's receiving heat as well, so this should be a positive quantity. We still have 1 kilogram. The C for water is 4,186 joules per kilogram per Kelvin. The change in the temperature, well, it ends up at 10 degrees centigrade, which is 283 Kelvin. And it started at 0 degrees centigrade, which is 273 Kelvin. So we can say that's T final minus T initial, and therefore it gives us a positive quantity, which is good, divided by the temperature of the lake, or the average temperature, which would be between 283 and 273, we could say 278. So 5 degrees centigrade is 278 Kelvin. And then finally, the lake. So this is equal to plus m 1 kilogram. Okay, now, wait a minute. What do we do here now? What's the mc delta T? Well, the amount of heat that's absorbed by the ice and the water is going to be the total amount of heat that's given away by the lake. So we have to take these two quantities into account and add them together. And since the lake is giving the heat away, it should be a negative quantity. So whatever we get here, we need to add those two up. And so that will be a minus 1 kilogram times 4,186, and I should stand somewhere where we can see what I'm doing, 4,186 joules per kilogram per, yeah, that's correct, times 80, and divide that by 273. And then we have to add to that this quantity right here, which is 1 kilogram, times 4,186 joules per kilogram per Kelvin, kilogram per Kelvin. And the difference in temperature, which is 10 Kelvin, and all divided by the average temperature, what that happened is 278. So notice that whatever heat was absorbed by the ice, it was absorbed by the cold water that now turns to the same temperature as the lake water. That same amount of energy is going to be given off by the lake, and since the lake is losing the heat, we need to put a negative in front of that, and we divide the whole thing by the temperature of the lake, which is 283 Kelvin, because the water of the lake will not really change in temperature. All right, so now we can go ahead and find each of these quantities. So the first one would be 4,186 times 80 divided by 273, and we see that is equal to 1,220. I'll round off to the nearest unit, so 7, that would be joules per Kelvin, a positive quantity, plus that one right there would be 4,186 times 10 divided by 278, and that would be 150.5, so we'll make it plus 151 joules per Kelvin. And then we have to add these two together. Oh no, we don't want to divide the whole thing by 283. I've already taken care of the temperature right here. I see what I'm doing wrong. I'm actually making a mistake. Because this is heat given off at the temperature of the lake, not the temperature of the ice. So actually, this temperature should be 283 Kelvin, and this should be 283 Kelvin. That's where I went wrong. So what I need to respect here is that the ice is at 273. The water, from the cold water from the ice, has an average temperature of 278, but as the lake is giving that heat away, it stays at a temperature of 283. So what I have to do there is actually divide those quantities by 283. So I get 4,186 times 80 divided by 283. So that would be minus a quantity of 1,183 joules per Kelvin. And then minus, that minus applies to there, so that's 4,186 times 10 divided by 283, which is 148, so minus 148 joules per Kelvin. There we go. So now you can see that heat added to the ice changes entropy by this much. Cold water being heated from 0 to 10 degrees centigrade changes entropy this much. The lake giving that heat away so the ice can be melted will reduce the entropy by this much, and the lake giving heat away so that the water can heat up is this much joules per Kelvin. Now when we add the whole thing together, we get 1227 plus 151 minus 1183 and minus 148. And the net entropy change when I add all that together, so delta S is going to be equal to 47 joules per Kelvin. And that's the total answer. Just so that we understand what we just did. Entropy change from melting the ice, we use the temperature of the ice. Entropy change for heating up the cold water from 0 to 10 degrees centigrade, from when the ice is melted to when it reaches the same temperature as the lake, we use the average temperature right here of 278. At the same time, the lake loses heat in order to melt the ice, in order to heat up the cold water. This is the entropy change for the lake losing the heat to melt the ice, but since the lake is at 283 Kelvin, we have to use the temperature of the lake. And then this is how much heat the lake loses to heat up that cold water. That was once ice, is now cold water. And again, the lake does it at a temperature of 283 Kelvin, 10 degrees centigrade. And then you can see that the negative entropy changes are smaller than the positive entropy changes, with a net entropy change that's positive of 47 joules per Kelvin. And that's how you do a problem like this. I told you at the beginning of the problem that this is tricky sometimes, and hopefully this example will help you see how to calculate the entropy change when the heat exchange between ice and a lake like that.